3 receipts, 3 summers, 3 times you paid for the exact same fix, and every single time the shop handed back your keys and told you it was good. It wasn't good. It was never good. Because the actual problem, a microscopic breach in your evaporator core, buried inside your dashboard, was never found. Never touched. Never fixed. Your mechanic has a word for you. They call you a seasonal customer. And today, we're going to make sure that season ends permanently. Let's start with something your mechanic almost certainly has not explained to you, and there's a very specific reason they haven't. Modern vehicles built from 2021 onward use a refrigerant called R134IF. It replaced the older R134A because it has a significantly lower global warming potential, which is good for the planet. But it comes with a trade-off that the industry quietly accepted and the consumer was never told about. R1234IF has a smaller molecular structure than its predecessor. It is physically more capable of escaping through gaps that R134A would never penetrate. Gaps so small, they're invisible to the naked eye. Gaps that pass a standard vacuum test without triggering any alarm. Gaps that your shop's UV dye test will never find. And where are these gaps most likely to form? Inside the evaporator core. The component buried deepest inside your dashboard. The one that costs between 6 and 9 hours of labor to access. The one that shops have a financial incentive to never diagnose correctly. Here's what the charge and release cycle looks like from a shop's perspective. A customer comes in with warm air. The technician hooks up the machine, adds refrigerant, charges for the service, and moves on to the next car. Total time, 20 minutes. Revenue, $250 to $320. Now here's the alternative. Properly diagnose the source of the leak. That means removing the dashboard, pulling the HVAC box, replacing the evaporator. We're talking 7 hours minimum. It's a difficult job that requires skill, time, and proper equipment. Shops that do volume work have every structural incentive to sell you the 20-minute solution and see you again next summer. This isn't a conspiracy. It's basic economics. But when you're the one sweating in your own car while your warranty argument is sitting expired in a drawer, it feels personal. Because it is. Today, we're going to find the leak they missed. And then we're going to fix it. Permanently, before we pull anything apart, I want to show you exactly why the standard diagnostic toolkit is inadequate for finding the leak we're hunting. Because if you walk into any shop and ask them to find an evaporator pinhole, this is what they're going to reach for. UV fluorescent dye. You inject it into the system with the refrigerant, run the AC, and then scan with an ultraviolet light looking for a greenish-yellow glow that indicates where refrigerant escaped. This method works extremely well for large leaks, a cracked hose, a loose fitting, a damaged Schrader valve. You'll see the dye pooled right there, glowing bright. But for a microscopic pinhole in an evaporator, a breach measured in microns, not millimeters, the refrigerant is escaping as a gas, not a liquid. There's no pooling. There's no accumulation. By the time enough dye migrates through a hole that small to be visible, you'd be waiting weeks. And even then, the dye is trapped inside the dashboard behind the HVAC box, inaccessible to a UV light being waved around the engine bay. Soap bubbles. The oldest trick in the book. You pressurize the system with nitrogen and brush soapy solution over joints and connections, looking for bubbles that indicate escaping gas. Again, perfectly valid for accessible large leaks. Completely useless for a component sealed inside a box, sealed inside a dashboard, that you cannot physically reach without disassembly. And here's the chemical problem that makes this even worse for modern vehicles. The UV dyes formulated for R134A systems are not fully compatible with R1234IF. The different chemical properties of the new refrigerant can cause older dye formulations to partially precipitate, meaning they can leave residue in your expansion valve or thermal expansion device. We've seen this contribute to reduced flow rates and inconsistent cooling in 2024 and 2025 model year vehicles. Some manufacturers explicitly void the AC warranty if unauthorized dye is introduced. Your shop probably isn't telling you that either. The leak we're looking for has a signature, not a visual one. An acoustic one. Pressurized gas escaping through a microscopic orifice creates an ultrasonic frequency high above the range of human hearing, completely invisible to every traditional test, but not invisible to this. Ultrasonic leak detection has been used in industrial refrigeration and HVAC for decades. It works on a simple principle. Escaping gas creates turbulence. Turbulence creates sound. At the molecular level, the friction of high-pressure refrigerant forcing through a microscopic gap generates ultrasonic waves in the 38 to 42 kilohertz range, depending on the system pressure and the size of the breach. This device translates those frequencies down into the audible range. What was silent becomes a distinct hiss, click, or crackling sound that changes in intensity as you move the wand closer to the source. We're going to run this vehicle's AC system right now with the engine on. The system is at operating pressure approximately 170 psi on the high side. If there is an active microscopic leak in this evaporator, the ultrasonic signature will tell us exactly which corner of the HVAC box to focus our disassembly on. Right there, lower passenger side of the evaporator core. The frequency spike is consistent with a sub-millimeter breach under operating pressure. This is the leak that has been robbing this owner of refrigerant for 3 consecutive summers. This is what $875 in recharge fees has been failing to fix. I want to be upfront about something before we start pulling panels. Dashboard disassembly is genuinely one of the more demanding DIY jobs in modern automotive repair. Not because any individual step is technically complex, most of it is just removing fasteners and carefully releasing plastic clips, but because modern interiors are designed for assembly efficiency, not serviceability. The engineers who laid out this dash were optimizing for how fast a robot could snap it together on a production line. They were not thinking about the person who needs to get back into it 3 years later. So we approached this methodically, with patience and with the right tools. Trim removal kit, bri tools, not metal, panel clip organizer trays, labeled Ziploc bags for fasteners, phone or camera for reference photos before each panel comes off, OHM service manual PDF open on a tablet. First rule of dashboard work: photograph everything before you remove it. Every connector, every clip location, every wire routing. You will not remember where things go after 4 hours inside this car. Your future self will thank your current self for the photos. The plastic clip situation on this generation is manageable once you understand the clip type. These are the quarter-turn expanding anchors. You need a 6mm flat blade to release them without snapping the head. We've seen shops use metal pry bars on these and leave a trail of broken clips that rattle for the rest of the vehicle's life. Take the extra 30 seconds per clip. It matters. And there's our HVAC box. The evaporator core is inside this housing, sealed from the factory. You can see immediately why standard detection methods can't find a leak in here. It's completely enclosed. There is no external surface to test. The only way to know what's happening inside is to listen for it ultrasonically or to open it. Look at this. Right here, lower corner, exactly where the ultrasonic detector pointed. You can see the corrosion bloom on the aluminum fins. This is the degradation pattern we see in vehicles that operate in high humidity environments with road salt exposure, or in areas with slightly acidic atmospheric particulates, which in 2026, after 2 years of elevated wildfire seasons, covers a significant portion of the country. The evaporator is aluminum. The condensation that forms on it during normal operation is slightly acidic pH around 5.5 to 6.0. Over years, the water sits in this lower pocket during the off-season. The aluminum corrodes, slowly, microscopically, until one summer, the wall is thin enough that system pressure finds a path through. Dealership quote for this repair on this specific vehicle, $1,840. That includes the OHM evaporator core at $340 and 9 hours of flag labor at $165 per hour. The aftermarket reinforced core we're installing today from a reputable manufacturer with a lifetime warranty cost $127. Our total additional parts cost for sealing components, O-rings, and new refrigerant $67. We're doing this repair for under $200 in parts. the replacement core goes in. But before we reconnect the refrigerant lines, there are two steps that separate a professional quality repair from a repair that fails in 18 months. Every refrigerant line connection uses rubber O-rings to seal the joint. On a vehicle that's been leaking and has had the system open before, even at a shop, those O-rings have experienced thermal cycling, chemical exposure, and potentially improper handling. Replace every single one, all of them. The O-ring kit for this vehicle is $14. The cost of skipping this step is another leak, potentially at a joint you just touched. Lubricate every new O-ring with clean PAG oil, the correct viscosity for your specific compressor, which is listed in your service manual. An O-ring installed dry will deform under pressure and leak within weeks. This is the step that separates a real repair from a recharge and release job. Before we add any refrigerant, we pull a deep vacuum on the system. We're targeting 500 microns or below on the vacuum gauge. This does two things. First, it boils off any moisture that entered the system during disassembly, because moisture in a refrigerant circuit forms acids that destroy your compressor and expansion. Second, it confirms the system holds vacuum before we put refrigerant in. If the vacuum rises after we isolate the pump, we have a leak. We find it now, not after charging. 490 microns. We isolate the pump. Gauge is stable. The system is holding. That evaporator seal is good. Now we charge. We're charging by weight, not by pressure, not by sight glass, not by feel. The ohm specified charge for this system is 500 grams of R1234YF. We're going to put in exactly 500 grams. Undercharging causes the compressor to run hot and lose lubrication. Overcharging causes high side pressure spikes and compressor damage. Weight is the only accurate method. 38 degrees Fahrenheit at the vent. In 87-degree ambient heat. That's exactly where this system should be. That's what this owner was paying for and not getting for 3 years. This repair took us 6 hours total. The parts cost $194. The dealership quote was $1,840. The 3 years of seasonal recharges this owner paid before today cost $875. With a proper diagnostic and a proper fix done the first time, this person would have been $2,521 ahead. Modern AC systems are not mysterious black boxes that only dealerships can service. They are engineered systems with knowable failure modes and fixable root causes. The only reason shops get away with the recharge cycle is because most owners don't know what questions to ask.